Standard Deviants present the supercharged world of chemistry.
Starring Galila Azraz, Gabrielle Smith, Jeremy Clavens, Dina Rubinson, Malcolm Smith, Trevor Dean, Chuck Hinshaw, Christiana Celeste, Tessa Monroe, and Chaz Masnick.
Ionic bonds form between two oppositely charged ions, and covalent bonds form when two atoms share an electron. Strong electronegative atoms pull the shared electrons in a covalent bond toward themselves, causing the molecule to become polar. Polar molecules have a slight positive charge on the less electronegative atom, and a slight negative charge on the more electronegative atom. And that is bonding.
Section C, bond energy. Bond energy, represented by the letters BE, refers to the energy needed to break or form bonds. A whole mole's worth of bonds, as a matter of fact.
Yes, we're back to the mole.
Say you have 1 mole of gaseous molecules, and the molecules are diatomic, which means that each of the molecules consists of 2 atoms. The bond energy is the amount of energy needed to break up 1 mole of the molecules into single atoms. So if you break 1 mole of diatomic molecules into 2 moles of atoms, the amount of energy it takes to do that is bond energy. Conversely, if the 2 moles of atoms bond to form 1 mole of diatomic molecules, the amount of energy released when the bonds form is also called bond energy. The stronger the bonds in a molecule, the more energy is needed to decompose the molecule into its atoms. As the number of bonds between 2 atoms increases, the bond energy also increases. That makes sense, right? More bonds, more bond energy. And here's the best part. Bond energy is another one of those cool things you can just look up in your textbook.
Oh, thank merciful heavens.
You can use bond energy to estimate how much heat will be gained or lost during a reaction. The heat gained or lost during a reaction is the reaction enthalpy.
So, to use bond energy to find the reaction enthalpy, you just add the bond energies of the bonds broken during the reaction, and from this value, you subtract the sum of the bond energies of the bonds that were formed.
Reaction enthalpy.
Here's what it looks like. This diagram shows the bonds in the following reaction. Chlorine gas plus methane gas make chloromethane gas plus hydrogen chloride. So in this reaction, 1 chlorine-chlorine bond breaks, and 1 hydrogen-carbon bond breaks. 1 chlorine-carbon bond forms, and 1 hydrogen-chlorine bond forms.
The reaction enthalpy, delta E, equals the sum of the bond energies of the bonds broken minus the sum of the bond energies of the bonds formed. In our case, delta E equals the sum of the energies of the bonds that break between a chlorine and a carbon and between a hydrogen and a carbon, minus the sum of the energies of bonds that are formed between a chlorine and a carbon and a hydrogen and a chlorine.
So find in your textbook the bond energy that's given off when 2 chlorine atoms break apart. That's 242 kilojoules. And add the energy given off when you break the bond between hydrogen and carbon, 413 kilojoules. And from that sum, subtract the sum of the energy given off when carbon and chlorine break apart, 328 kilojoules, plus the energy given off when hydrogen and chlorine break apart, 431 kilojoules. Gives us 655 kilojoules minus 759 kilojoules. The enthalpy of this reaction is negative 104 kilojoules.
So, bond energy is the energy needed to break or form bonds. You can look up bond energies in your book and use those values to calculate how much heat will be gained or lost in a reaction.
Lewis structures, also called electron dot structures, use dots to show the number of electrons in the outer shell, known as the valence shell of an atom, indicating the bonding pattern between atoms that form a compound. When we draw the Lewis structure of an atom, we have to consider the octet rule. According to the octet rule, when a compound forms, an atom gains or loses electrons, or shares pairs of electrons until it has 8 electrons in its valence, or outer shell. An atom with 8 electrons in its valence shell is a happy atom. A couple exceptions to the octet rule are hydrogen and boron. Bond energy, represented by the letters Be, refers to the energy needed to break or form bonds. You can use bond energy to estimate how much heat will be gained or lost during a reaction. The heat gained or lost during a reaction is the reaction enthalpy. You can look up bond energies in your book and use those values to calculate how much heat will be gained or lost in a reaction.
Part 1. Molecular Geometry and Bonding Theories.
No, molecular geometry.
Molecules come in a variety of different shapes. Molecular geometry is the geometric arrangement of the atoms in molecules and in covalently bonded crystals. When you see those funky models of strange molecules that look like kids' building toys, those are there to help you understand molecular geometry.
The two types of bonds, ionic bonds and covalent bonds, form different structures. Ions attract as many ions of opposite charge as they can pack around them. Covalent bonds are a little different. Two covalently bonded atoms share a pair of electrons, and the bond is called a directional bond, since the arrangement of covalently bonded atoms is more neat and specific. They are not just all crammed together.
Section A, the VSEPR theory.
Scientists have developed a number of theories about how atoms arrange themselves in a molecule. The shape the atoms form in a molecule is called molecular geometry. A common model used to predict molecular geometry is the valence shell electron pair repulsion model, known as the VSEPR model. The VSEPR model predicts molecular geometry by describing how electron pairs bond and theorizing how electron pairs and bonds will affect the shape of the molecule. According to the VSEPR model, the electron pairs in a molecule's valence shell are arranged so that they're as far away from each other as possible. In other words, the electrons act like they repel each other.
Whenever you're trying to predict molecular geometry, be sure to VSEPR.
The VSEPR model says that a molecule with two pairs of shared electrons has a linear shape. Using the VSEPR theory, if you know that a molecule has two pairs of shared electrons, you can predict that the molecule will have a linear shape. This linear-shaped molecule is represented by the notation AX sub 2. The sub 2 tells you that there are two pairs of shared electrons.
AX sub 2. Linear!
A molecule with 3 pairs of shared electrons is called trigonal. And here's a picture of what the VSEPR theory says it looks like. Trigonal molecules, those that have 3 pairs of shared electrons, are represented by the notation AX sub 3. The sub 3 tells you that the molecule has 3 pairs of shared electrons.
Molecules can also have non-bonding electron pairs. The non-bonding electron pair takes the place that a regular bond would occupy. We will use water again as an example, but know that this example shows you only one of the many possible arrangements of bonds and atoms. Be sure to check out the others in your textbook.
I'm checking out the other arrangements in my textbook.
Water has 2 bonds between hydrogen and oxygen, but oxygen also has 2 non-bonding electron pairs. This gives water a tetrahedral arrangement of electron pairs and bonds. Since diagrams don't usually show the non-bonding electrons of oxygen, we usually just say that the water molecule is bent rather than referring to it as tetrahedral.
That's bent, bent, bent.
The geometric arrangement of the bonds in a molecule, along with the electronegativities of the atoms, or how strongly some of the atoms hog the shared electrons, determine the molecule's polarity.
As we mentioned before, a molecule made of two different atoms with different electronegativities is held together with polar covalent bonds. The atom with greater electronegativity is a bigger electron hog, so it creates a slightly negative charge for itself and a slight positive charge for the atom it's supposed to be sharing electrons with. This arrangement forms what we call a dipole. Dipole molecules have slightly positive and slightly negative regions on them, but they are still considered neutral molecules. The small charges on regions of the molecule just affect the way a group of these molecules would line up alongside each other. Dipole molecules tend to line up so that the negative part of one molecule pairs with the positive part of the next. These attractions between polar molecules are known as dipole-dipole forces. We'll talk more about dipole-dipole forces later.
Dipole.
Dipole.
So you don't need a protractor to figure out molecular geometry. The VSEPR theory predicts the shape of molecules based on their bonds. The position of electrons affects the shape and behavior of molecules. This is certainly true with polar molecules, which have an electronegative atom that hogs the electrons and gives itself a slightly negative charge, and the atoms around it a slightly positive charge. Water molecules, for example, stick together because they are polar. It all comes back to the placement of those electrons.
Section B, orbital overlap.
There are two accepted theories about how atoms bond together to form a molecule. They are called hybrid orbital theory and molecular orbital theory. The two theories try to explain pretty much the same thing, how molecules hold together, but each explanation is just a little different. We'll tell you about hybrid orbitals first.
So you understand a bit about orbitals, how an atom's electrons move around its nucleus, right? Well, when molecules form, the orbitals of the component atoms overlap with each other to form hybrid orbitals, mixtures of the overlapping atomic orbitals. These overlapping, or hybrid orbitals, let two electrons with opposite spins come together to form a covalent bond that helps hold the molecule together. Hybrid orbitals, like atomic orbitals, can only hold two electrons each. So mixing two atomic orbitals creates two hybrid orbitals.
A molecule's Lewis structure shows you how many hybrid orbitals the molecule will need in order to accommodate all its bonds and unbonded electron pairs. Some combination of the atom's outer or valence orbitals will combine to form the hybrid orbitals.
In 1910, farmer Otis Springwald, whose favorite foods were beef and chicken, experimented with combining beef and poultry. After 17 years of hard work, he introduced the cow chicken.
So, you need a hybrid orbital for each bonded and unbonded pair of electrons in a molecule. For example, here's the Lewis structure for beryllium hydride. Beryllium is the central atom and the hydrogens are bonded to it. According to the Lewis structure, there are two bonds that need to be accommodated by hybrid orbitals, so there will be two hybrid orbitals.
Now let's look at the orbital diagram for beryllium. Beryllium's electrons fill up one s and two s orbitals. Here's hydrogen's orbital diagram. It only has a single electron in the 1s orbital, so we have two hydrogens, each with a single electron in its 1s orbital. Now we want to set this up so each of hydrogen electrons can bond with one of beryllium's electrons, and each bonded pair gets a hybrid orbital of its own.
There's a real neat trick we can do to arrange beryllium's electrons in such a way that they can bond with hydrogen's electrons. We can promote an electron from the 2s orbital to the 2p orbital, and now beryllium's orbital diagram looks like this. Now there's only one electron in the 2s orbital and one electron in the 2p orbital. Beryllium's s and p orbitals mix to form two sp hybrid orbitals. These sp hybrid orbitals can bond with hydrogen's orbitals.
These hybrid orbitals will always arrange themselves as far from each other as possible. And in this case, the orbitals are 180 degrees from each other.
You just stay over there on your side.
Conveniently, there's an easy way to figure out how many hybrid orbitals will form in a molecule.
A molecule's hybrid orbital number will tell you how many hybrid orbitals the molecule needs. The hybrid orbital number is the number of bonds and unbonded electron pairs that form around the atom in the center of the molecule. When you count bonds for hybrid orbital numbers, double and triple bonds count as a single bond. This chart will tell you how the orbitals will hybridize based on the hybrid orbital number. Yippee!
Yippee!
Yippee! Now let's decide how the hybrid orbitals will form around boron in the compound boron trifluoride, BF3. We'll start by looking at the Lewis structure for BF3. Count the number of single bonds and the lone electron pairs around boron, the atom in the center. We see 3 single bonds and no lone pairs, so the hybrid orbital number is 3. Now look at the chart. To accommodate the 3 bonds, we need 3 sp² hybrid orbitals.
BF3's 3 bonds form a trigonal planar arrangement.
Methane, CH4, forms a 3-dimensional molecule. You can tell by the Lewis structure that methane has 4 single bonds. Check the handy chart and you'll see that 4 bonds gives methane a hybrid orbital number of 4 and a 3-dimensional tetrahedral arrangement.
Now on to molecular orbitals. Molecular orbital theory is another model that explains how molecules hang together. The orbitals from the atoms in the molecule overlap to form covalent bonds that glue the atoms together. When 2 atomic orbitals overlap, they form 2 molecular orbitals. Let's look at hydrogen, for example.
The 2 overlapping 1s hydrogen orbitals form 2 molecular orbitals, one with high energy and one with low energy. The low energy bonding molecular orbital forms the covalent bond that holds the nuclei together. The friendly bonding electrons in the bonding molecular orbital crowd between the 2 hydrogen nuclei and join in the covalent bond that holds the atoms together. The high energy anti-bonding molecular orbital doesn't help hold the molecule together. This orbital not only has fewer electrons, but the high energy and bad attitudes of the anti-bonding electrons keep them from bonding with each other. Each molecular orbital can hold 2 electrons with opposite spins, just like atomic orbitals.
In the molecular orbital theory, the term bond order refers to another way of counting bonds between 2 atoms and a molecule. More bonds make a more stable molecule, so a high bond order number indicates a molecule that'll hold together pretty well. To find bond order, subtract the number of antibonding electrons in the molecular orbital from the number of bonding electrons. Then divide that number in half. Now you divide it in half because you're counting the number of pairs, not the number of single electrons.
Calculating bond order is pretty easy. Let's go back to the hydrogen example. Hydrogen has 2 bonding electrons and 0 anti-bonding electrons. So the equation we'll use to find hydrogen's bond order looks like this. 1/2 of the quantity 2 minus 0 equals 1. The bond order for hydrogen is 1.
Hold it. How do I know how many bonding electrons and how many anti-bonding electrons there are?
Glad you asked. It's not too hard, actually. Remember that each orbital can only hold 2 electrons, and electrons will always go to the lowest energy orbital first. So, count up the number of electrons you need to accommodate. Let's say the molecule has 5 electrons. 2 will go to the first bonding molecular orbital, the next 2 will go to the first anti-bonding molecular orbital, and the 5th will go to the second bonding molecular orbital. So, there are a total of 3 bonding electrons and 2 anti-bonding electrons. Say your molecule has a total of 8 electrons to accommodate. 2 will go to the first bonding molecular orbital, 2 will go to the first anti-bonding molecular orbital, 2 will go to the second bonding molecular orbital, and 2 will go to the second anti-bonding molecular orbital. So, in this case, you have 4 bonding electrons and 4 anti-bonding electrons.
So, there are 2 models that explain how molecules hold together: the hybrid orbital theory and the molecular orbital theory. Hybrid orbital theory says that when the orbitals of 2 atoms in a molecule overlap, they form a covalent bond that holds the molecule together. The number of orbitals that overlap depend on how many need to overlap to accommodate all the pairs of bonded and unbonded electrons. Molecular orbital theory says that when two orbitals come together, one from one atom and one from another, two new orbitals will be formed, one with low energy and one with high energy. The low energy or bonding molecular orbital forms a covalent bond that holds the molecule together. The high energy or anti-bonding molecular orbital does not help hold the molecule together at all.
The VSEPR model is a common model used to predict molecular geometry by describing how electron pairs bond and theorizing how electron pairs and bonds affect the shape of a molecule. According to the VSEPR model, the electron pairs in a molecule's valence shell are arranged so that they are as far away from each other as possible. In other words, the electrons act like they repel each other, affecting the shape of a molecule. There are two accepted theories about how atoms bond together to form a molecule: the hybrid orbital theory and molecular orbital theory. According to the hybrid orbital theory, when molecules form, the orbitals of the component atoms overlap with each other to form hybrid orbitals, mixtures of the overlapping atomic orbitals. These overlapping or hybrid orbitals let two electrons with opposite spins come together to form a covalent bond that helps hold the molecule together. According to molecular orbital theory, the orbitals from the atoms in the molecule overlap to form covalent bonds that glue the atoms together.
Part 2. Gases.
You know lots about gases. Take a deep breath. Go ahead. You just sucked up a bunch of gaseous molecules, not to mention a few dust mites. Elements that make up the air you breathe, like nitrogen and oxygen, are gases under ordinary conditions, or the normal conditions of the Earth's climate. Some substances, like water, can be in a liquid, solid, or gaseous state under ordinary conditions. For instance, if you have a closed container of ice water, there is ice, the solid, water, the liquid, and water vapor, which is the gas formed by evaporating water. So it's got all three.
Gases act differently than solids or liquids. For one thing, they expand and compress real easily. If you put a little gas in a container, like my helium tank, the gaseous atoms, or molecules, will move away from each other to fill up the whole container. If you want to, you can put a lot of gas in this tank because the gaseous atoms, or molecules, will pack real close together to allow more atoms in.
We describe gases based on these four properties: mass, volume, pressure, and temperature. We'll use grams and kilograms to measure the mass, and liters and milliliters for volume.
The pressure of a gas is the force it exerts on a unit of area. In other words, when we measure the pressure of a gas, we're measuring how hard the gas is pushing on the stuff around it. Atmospheric pressure is the force exerted by the atmosphere on a unit of the Earth's surface. As we said before, the unit used to measure pressure is the atmosphere. So don't confuse the unit, atmosphere, with the term atmospheric pressure.
Kelvin is the temperature unit you need for gas equations. When you're talking about temperature on the Kelvin scale, don't refer to it as degrees Kelvin. The units are not degrees. They're simply called kelvins. Your professor might ask you to calculate a problem involving gases and give you the temperature in degrees Celsius. Don't fall for that old trick. Just convert to kelvins. It's real easy. You just add 273.15 to the Celsius reading. So, 0 degrees Celsius equals 273.15 kelvins. 22 degrees Celsius equals 295.15 kelvins, and so on. You get the picture.